nothing like that. So hopefully this won't be too hard for you. But again, it is important because to truly understand, I'm thinking right now, because I try to talk to my friends, but they have questions about COVID stuff. So some of them come to me because they know I understand this kind of stuff. So for me to fully explain how the COVID-19 vaccine works, before that, I have to teach them how mRNA works. And before they can even understand that, they need to understand how DNA works. And before they can truly understand that, they need to know how chemistry works. So again, this goes back to why you're getting a bachelor's degree, right? You need all this basic knowledge to be able to understand more important, more specific things. So here we go. Chapter 2, Essential Chemistry for Biology. Again, like I said, chapter 1, every chapter starts with this. It's a little guessing game. We don't really have time as usual, so I'm going to skip it, but I will at least tell you what it's about. There's some fries. Obviously, they're putting salt on the fries. Your book uses that example. It's really cool because salt is sodium chloride. And one of the big things people use to try to scare you about chemicals and chemistry in general is like they'll give you some, there's this chemical in this product. It's scary. You shouldn't get it. And you should instead buy my organic essential oils or whatever. And it's funny because they try to scare you with stuff. And if you don't know chemistry, it can be scary. So obviously everyone knows salt, and you probably even know that it's called sodium chloride. But if you didn't, I could say this stuff right here is dangerous because sodium, it's an explosive metal, and it is. And chlorine gas is used to kill people, and it is. So separately, those things are deadly and dangerous. But together, they're salt, and it's delicious, and you do need small amounts of it. Up there is coral bleaching. We'll talk about that later. And then right there's some copper pipes. I don't know why they use copper as an example because we don't talk much about copper in this chapter. But anyway, let's move on. That's not going to be on the exam. I'm also not going to ask you about radioactivity, and I don't really understand why your book talks about radioactivity. I'm going to breeze over this, but even if you don't understand this, you're going to be all right through the rest of the semester because moving past this chapter, we'll never talk about radioactivity again, I don't think. Anyway, but because it's in your book, and I teach out of the book because it's a 100 level class, I'm going to talk about it very quickly. Radioactivity, that's the emission of high energy particles. Those high energy particles can penetrate living tissues. That's how high energy they are. Even though they're small and invisible, they're very energetic, and they can kill cells by damaging your DNA. So that's how radioactivity is bad, right? Because if it gets in there and destroys your DNA, if it's really bad, it'll just kill you almost immediately. If it's just small damage to your DNA, then that can cause things like cancer and stuff like that. So later in the semester, when we learn about genes and how they work, you'll understand that obviously one small change to your DNA could be deadly. So yeah, it can be bad. But your book points out that it can also be good. Radiation is also medically beneficial because you can use it to treat and diagnose disease. I know this because my mom had brain, sinus, and skull cancer all at once. And the way they treated it, well, among other things, was radiation. So they went in there and precisely put it where it needed to be to kill those cancer cells. So here's an example of bad radiation, right? When is it dangerous? Can anybody take a guess? Obviously, you can see some pictures. I don't mean when specifically, like, oh, yeah, it was dangerous in Hiroshima, which was August. What was that, August 12th? Anyway, yes, it's dangerous in nuclear bombs, but specifically when there's two things that you could say that makes radiation dangerous as opposed to when it's beneficial. Can anybody guess what the two things might be? Like what's happening in a nuclear bomb versus using radiation for a medical treatment, or what's happening in a nuclear bomb versus what's happening in a nuclear power plant? Direction? Yeah, that's one of them. Yeah, especially in the medicine. It's very directed in the medicine. Yes?
Isn't a nuclear bomb, doesn't it create like a chain reaction of like that's not what is supposed to happen in nuclear power plants?
Perfect. It's uncontrolled. Yes, uncontrolled. So it is a chain reaction and it keeps going. And that's where you get all this huge release of energy. In a nuclear power plant, it's controlled. So yes, they keep splitting, but there's ways to keep it from like keep getting out of control. So yeah, it's bad if it's uncontrolled. It's also bad if it's not precise, like he was saying. For medicine, it's very precise. It's controlled. You're going towards that one small spot. So if it's uncontrolled and it covers most or all of your body, it's bad, right? And again, this is just an example. There will be no questions on the exam. There might be some questions on the study guide. I don't remember. So any questions about this slide? All right, we can also use radioactive isotopes as tracers. So when you get things like a PET scan or MRI, things like that, that's how that works. You'll learn about what an isotope is. That's also why your book does this at the beginning of the chapter, like throw out some words you might not know of, like, and they think you're going to be interested in, like, oh, radioactive isotopes. That's fascinating. I can't wait to learn what an isotope is. And you will. You'll learn what an isotope is. But anyway, some of them are radioactive, and because of that, when you look at them with certain machinery, they will show up. That's all that says. Again, not on the exam. Again, like we already talked about, radiation therapy for cancer. It's funny because that's very much, this picture's from your book, but that's very much what it looked like for my mom. She had like that white mask. And like I said, it was brain, sinus, and skull cancer. So that's close to where they did it for her. But again, it's very precise, and they control the amount of radiation. Yes, sir.
What is that white mask?
That mask, I don't know. So for those of you online, he asked what the white mask does, and you might not be able to see that, but you have PowerPoints online. I think it just makes it more precise where they can zero in on exactly where it needs to be. But I don't know that. That's a great question for independent work if anybody wants to look that up. That could be a 3-sentence independent work, right? What is the purpose of that? According to the Mayo Clinic, the purpose is this. Boom, done. You didn't get many points, but that's okay. Yes, sir.
Nuclear energy is supposed to be like super clean.
Yes. So the question was, is nuclear energy super clean? And it sort of is. And I say sort of because the dirty part is extracting the uranium and obviously transporting it. And then after you've used it, there's radioactive waste that you have to deal with. But there's new technologies too that are coming up with ways to utilize that radioactive waste. And it turns out that the process we use, it actually stops earlier than it needs to. Like, so when you break uranium down, it turns into other things, other elements. But we could still use those elements. We just don't. And I don't have time to get into it. So good question. And then again, something you could look up for independent work if you want. Yeah. Any other questions? Okay. Obviously, too, the other thing about nuclear energy that everyone's afraid of is accidents. Nuclear meltdown, like Chernobyl, or when you get a big flood like Fukushima, and then it spreads everywhere. But even that's not as bad as everyone thinks. Again, something you can look up if you want to for independent work. So again, your book's posing these questions to make you think, stuff to keep in the back of your mind as we go into this chapter, not because you're going to be tested on it, because again, your book is trying to spark some interest into this chapter and why it's relevant to your everyday life. But what makes something radioactive, right? That's something you should consider. I'll answer that question if you want some other time, but you're not going to be tested on it, and you don't need to know it for the rest of the semester. So I'm not going to answer it right now. Many questions about life are reduced to questions about chemistry or chemicals and their interactions. So that's why you're learning about chemistry in a biology class. And the knowledge of chemistry is essential to understanding biology. That is so true. You're going to see throughout the semester, as I teach you something, I'm going to come back to this chapter. I'm like, don't forget, this is happening because of this. And I'll take it back a little bit, which is happening because of this. And ultimately, it all comes back to this. And if you've ever had physics, ultimately, chemistry goes back to physics. So it's funny how all that works. Any questions so far? Good. You guys are easy. Yeah, this is the picture we already saw. Helpful radiation. Hooray, that's somebody's brain. So here we go. This chapter is broken down into two main portions. There's going to be, that's hard to read, isn't it? Some basic chemistry, which is the top one, right? That's what we're going to talk about first. And then later we will talk about water and life. Obviously, water is important to life. I'm sure you know that, but we're going to learn why. So here we go. Some basic chemistry. Again, like we already said, and your book keeps saying it, so will I. If you take it apart any biological system, so whether we're talking about an ecosystem or a population or an organism or an organ or a tissue, whatever it is, if you break it down, eventually you're going to come to chemistry. And chemistry is always happening in your body. No need to write any of that down. Sorry, I should have preempted that before I put it up there, but this is just an introduction to what we're about to talk about. That's one of my favorite chemicals. I don't know if you guys can read it. Caffeine. That's what it looks like. Does anybody have any questions so far? I'll slow it down once we start getting to the parts that are really important regarding the exam and what you need to know moving forward, which is now. Now we're going to talk about the most basic level, at least for us. We're going to talk about matter, which consists of elements and compounds. So does anybody know what matter is? And by the way, I don't come up with these memes. I don't even look for them. I just find them, and when I find them, if they're relevant, I include them on include them on our PowerPoints. But anyway, Does anybody know what matter is? Can someone please try to define matter? Remember, don't feel bad if you got the wrong answer. That's fine. Yes, sir.
Matter of substance that takes up space.
Basically, yeah. Even the substance is maybe even extra. It is anything that occupies space and has mass. So like the substance, you could say has mass, right? So yes, you should just know matter is basically stuff. That's what it is. Matter is stuff. I am matter. This thing is matter.
What's the matter?
Yeah. It don't matter if you don't mind. Yeah, even the air that we can't see right now, that is stuff, right? That is matter. And you might think you can't feel it, but you can. It's there. Matter comes in 3 stages or 3 states, and I'm sure you know what they are. Does anybody know the 3 states of matter? And the most common example is the different states of water. Yes, sir. Yeah, solid, liquid, and gas. That's so easy, I probably will not ask you that on the exam. This is not middle school. I think even my elementary school son knows that. So anyway, matter is anything that occupies space and has mass. So that, and also there's a meme about mass. So what is mass? Does anybody know what mass is? And not midnight mass before Christmas or whatever. What is mass? That's one of those things where there's so many definitions of biology where like in chemistry, we're like, I know what that is, but now how do I put that into words? So can anybody put that into words? What is mass? No guesses? Yes.
Probably not the answer you're looking for.
That's okay.
Is it like the weight?
Mass. For those of you online, he said mass has weight. Thornabar, did you have an answer? And he's on the right track, by the way.
Yeah, I say mass is the amount of space that matter.
Yeah, and you two kind of said the same thing in different ways. He said the weight, you said the amount, and that's true. It's the measure of the amount. So exactly what you said, Anthony. That's correct. It is it's the measure of the amount of a material in an object. And so one of the ways you can measure that is with weight. You got to also measure it by volume. You could also literally measure it by how many atoms there are or how many molecules. We won't do that. That's a lot of math. But yeah, so math is anything matter is basically stuff, right? It occupies space. It has mass. What is mass? It's the amount of stuff. And it's funny, we usually talk, when we talk about weight, we usually talk about pounds or kilograms. And when you break that down into physics, really what you're looking at there is force, pounds and kilograms. Well, that's not necessarily true. I don't want to confuse you. This isn't a physics class. Let's just leave it at that. So we know what matter is. We know what mass is. Does anybody know what an element is? I'm sure you all do. So I guess the better question is, can anybody put it into words? What is an element? And I'm not talking about the Honda element, the vehicle. What is an element? I like that. Basic, the most basic, yep. And in our class, that is the most basic. An element cannot be broken down into other substances by chemical reactions. Meaning, let's use a diamond, for example. Diamond's pretty big, right? And a diamond is only one element. It's only carbon. So you can keep breaking diamond down. You can break, it's gonna be really hard, but if you were to break a diamond down, no matter how many times you break it, eventually you're just gonna end up with one carbon atom, right? And you cannot break that down any farther chemically. Now you could break it down radioactively and things like that. But once you've done that, it is no longer carbon. We'll talk about that later. So an element is something that cannot be broken down into any other substances by chemical reactions. So like, for example, like since we've already talked about the nuclear power thing, uranium is an element. You cannot break that down chemically and make anything else. Now you can split it, and that's radioactivity, right? You can split it other ways, not chemically, and then turn it into other elements. But with chemical reactions, you cannot break it down anymore. So to wrap all this up until one page up, all matter is composed of elements. In another way, your book doesn't say this, but I like to say it because you need to know this. Matter is also a chemical. So everything is a chemical. Everything in you is a chemical. Everything you eat is a chemical. So that's another funny thing I see with some that crap I see with people trying to sell you garbage and say, well, this is chemical free. I'm like, well, that's a lie unless they're selling you a vacuum. Everything is a chemical, so nothing is chemical free. What they probably mean is it doesn't have any dangerous chemicals or artificial chemicals, but that's another story. Any questions about this very important slide? This is a very, very important slide. There's no fat on this slide. You need to know nearly everything on here other than the meme. All right, moving forward. This is just for your own information. None of this will be on the exam, but there are 92 naturally occurring elements. If you look at the back, you can see the periodic table. That upper block is those 92. Below that is some other elements that are not naturally occurring. That's why they don't count in the 92. Your book gives some examples out of 92. I don't know how they chose their examples, but the examples they gave that you do not need to know for the exam necessarily was carbon, oxygen, potassium, and gold. Well, I guess I can see why they picked those. We all know all four of those. Carbon and oxygen, we're going to talk about a lot in this chapter. Potassium, you know that you need that. And we're also going to talk about that a little bit in this chapter. And obviously gold is valuable, so maybe that's why they chose that. Each symbol in the periodic table, and again, if you look back there, you can see it. You know, like carbon is C, nitrogen is N, helium is He, so on and so forth. Each one is derived from English, Latin, or a German name. You do not need to know that. Also, another thing, for the most part, you do not need to know any of the symbols, other than a select few, and you'll understand those that you need to know as we get to it. But don't go home and like start studying the periodic table. Any questions about this slide? Okay. Oh, also the chemical symbol for potassium is K. Hence the joke there. Can you tell a potassium joke? Okay. All right. Here's an example of the periodic table. The atomic number, and there's no need to write this down yet either because we will talk about it in this chapter, but you can see there, they use carbon as an example. The atomic number is 6, which is almost always found on the top. Then you have the big element symbol in the middle, which is C in this case. And then the atomic mass, which is the mass average, and we'll talk about that later. And for carbon, that is 12.01. So again, this is just an example. You do need to know, like if I were to give you something, you don't need to memorize that carbon is 6 and 12.01, but you will need to know that the top is the atomic number, the bottom is atomic mass, and the middle is the symbol. But we will cover that later in the chapter. Right now, it's just an example. Any questions? Sometimes I like to have fun in this chapter because I think this is, based on the feedback I get, this is the most boring chapter for most people. So I try to have more fun with it, or we're a little bit short on time, so I'm not going to do it this time. I like to play a guessing game where I'm like, hey, can you guess this element? That one's mercury. The way you can tell is because it's melted metal, right? Plus that little Hg, that's mercury. Plus it looks like Freddie Mercury. And then you've got a bunch of copper, and that's David Copperfield. And then you have a bunch of lead, and those are the symbols for Led Zeppelin. Iron, and then obviously you've got that Fe, which is the symbol for iron, and the thing looks like Iron Man. Sorry we didn't play the game, but again, we're short on time. All right, now back to the book. Here's what you do need to know. Not this number, but there are 25 elements that are essential to people. And what we're going to do is we're going to look at all 25 of those. And those themselves are going to be broken down in the subcategories. And you do need to know a good portion of this. Again, I'm not going to ask you how many elements are essential to people. I'm just telling you right now that we're about to talk about 25 elements. Then there's the big four. And they make up about 96% of your body weight. You do need to know the big four. You don't necessarily need to know that number that makes up about 96%. Just remember, the reason we call it the big four, I mean, think about that. The elements I'm about to tell you make up 96% of who you are. The other 4% is the other 21 elements. So that's a lot, right? That's why I call it the big four. Can anyone guess what these big four might be? Just think about life in general. Even if you're not, you might even be better off if you're not a biologist or a chemist. Because if you're not, you might only know a few elements. So you might just think, oh, it's these. Yes.
Oxygen, hydrogen, carbon, sodium.
Good guess. Three of them are on there, and we will talk about sodium later. That's one of the 25, but not the four. So great. Nitrogen, oxygen. What else did you say?
The carbon, oxygen.
Carbon, nitrogen, oxygen. Yeah. What's the other one? Any guesses? This one's a little bit less intuitive, but it's hydrogen. So yes, know these. Oxygen, carbon, hydrogen, nitrogen. Those are the big four. You do not necessarily need to know them in any order. Just know that those are the big four. And I would say study that, but you don't need to, because when we go in lab and all the chemistry discussions we're going to have, you're going to see those way more than anything else. So those are just going to hopefully stick in your brain without any effort. So yes, because of the big four and because we're going to talk about them so much, you should also know their symbols. Luckily for you, it's one of those easy ones. It's not like gold, which is AU, or mercury, which is Hg, right? Those don't make any sense. Or potassium, which is K. These all make sense. Oxygen O, carbon C, hydrogen H, nitrogen N. So any questions about the big four? All right, so let's talk about the other 4%. Your book mentions that the other 4% is made up mostly of 7 elements. You don't need to know that number. Just letting you know that we talked about the big four. Now we're focused on the other 4%, right? And we're saying of that 4%, most of that is made up of 7 elements. Again, you don't need to know the number. You don't need to know all 7 elements. And your book only talks about a few of them. So I'm only going to talk about the ones that they talked about. The first one is calcium. I'm sure you guys have heard of calcium. Do you know what it's used for in your body or where you can get it? Not that I'm going to ask you that on the exam, but it's in your book. So let's talk about it. Yes, sir.
Milk.
Yep, you can get it in milk. Where else? Or how is it used in your body?
To strengthen bones. And I guess overall muscle scarlet sort of thing.
Yep. So calcium is important for bones and teeth, among other things. There's so many other things, but those are the big ones. And like he said, milk, right? Milk's a dairy product. You can also find it in sardines, green and leafy vegetables. This is not a nutrition class. This is not a health class. So if you're taking notes, I would rest your hand because I'm not going to ask you this. But yeah, calcium is an example. Another example is phosphorus. Does anybody know how that's used in our body or where you can get it? That's a tougher one, right? Yes.
It's the component of DNA.
Yes, you'll learn about that. It's also the component of ATP, which I don't even think your book mentions in this chapter. But ATP is so important, and we'll talk about that later. Yeah, it's part of your DNA. So without phosphorus, you wouldn't have DNA, meaning you just wouldn't be here. You can find it in eggs and beans and nuts. Again, not going to be on the exam. So this bottom, oh yeah, that's a misprint. Do not see the upcoming slide for the other 5 elements because we're not going to talk about the other 5 elements because your book doesn't discuss the other 5 elements. So for independent work, if you want, look at your book, look at those other 5 elements and just answer those basic questions. Why are they important to your body? And where can you find them? Here's another thing you can look into because people will say this too often. Oh, that's a poison. Don't buy that. That's a poison. There's poison in that vaccine, blah, 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 blah. I'll tell you this, and your book doesn't talk about it. Everything's a poison. Everything is poisonous. It's all about the dose. So if you look up any of this, you need all of this, but how much is too much? How much is too much calcium? Like at what point does it become a poison? And then also the follow-up question to that would be, well, what happens when you have too much of it? So that's something to keep in the back of your mind. Look into it if you want for independent work. And what I just said is even more relevant to this. There's also, so again, we've talked about 96% is the big 4. And now we're still talking about the other 4%, right? And of the other 4%, most of that is made up of 7 other ones. And we talked about 2 of the 7. Now we're talking about even smaller amounts. Less than 0.01% of your weight is made up of 14 trace elements. And that's why they're called trace elements. It's not because they're hard to find in nature, but they're required in very small amounts in your body. So again, all of those 14, each one of them adds up to 0.01%. Not a number that you need to know for the exam. The point is you need a very small amount, which goes back to what I was saying earlier. Everything's a poison, right? So these especially, you need a very small amount. So how much is too much? And what happens if you have too much? For that matter, what happens if you don't have enough? It's things you can look at for independent work. So when someone says like fluoride's a poison, yeah, it is. Everything's a poison if you have too much. Anyway, so know that there's a very small amount. That's what trace elements are. Know that they are essential. Your book gives some examples. And again, you don't need to know these. These are just examples. Your book talks about iodine. It's if you have an iodine deficiency, that causes goiter, which is an enlarged thyroid. The lighting is kind of off, so I don't know if you can see, but she's got this really large lump on her neck. That's a goiter. She's very unhappy about it, as you can tell. How do you get iodine? Well, it's found in green vegetables, eggs, seafood, dairy products, and iodized salt. So I'm sure if you've ever seen something that says iodized salt, that's what they mean by iodized. They literally put iodine in your salt so you can get it because you need it. And again, I'm not going to ask you any questions about iodine. It's just an example. Any questions about that? All right, fluorine's the other example your book gives. It's added to dental products, right, like toothpaste, sometimes mouthwash. It's added to your drinking water, at least in most places in America. Other places, not so much. I lived in Japan. I know it wasn't in our drinking water where I lived, and I don't think it was anywhere else in the country either. And you could tell. Anyway, what does fluorine do? It helps maintain healthy bones and teeth. Obviously, this guy looks like he might not get much fluorine, but at least he's happy. It's not bothering him. And again, that's just an example. You do not need to know anything about fluorine for the exam. And again, people will say all the time, because this is a conspiracy theory about everything, they're putting fluorine in your drinking water. The government trying to kill you, and they might be, I don't know, but they're not doing it with fluorine. And you can look up what are the deadly levels of fluorine.
Is it fluorine the stuff that Alex Jones talks about putting in the water to turn the frogs gay?
Probably. Oh, really? Is that what it is? To turn the frogs gay? Nothing worse than a gay frog. A gay salamander, I'm okay with. The frogs, it's just too much, man. Too much. Don't quote me on that. Anyway, no, I don't know. I just know there's conspiracy theories, and I try not to dig too deep into them. I should though, because I want to learn, even though it's false. Anyway, that's fluorine. That's an example. Here's some really interesting stuff, in my opinion. You could look into this. We have less than a minute. Let me hurry up. If you download this PowerPoint, you can click on these links. So there's a video. Have you ever seen where it says something says it's fortified with iron? That's because they're literally putting iron, like the stuff that makes steel, in your food because you need it. So if you click that video, there's two different videos. There's one person who's like showing you, look, if you blend this up in water, you can put a magnet to your cereal and the metal will come to the magnet. And he says it as a matter of fact thing. And then someone else is like, they're putting metal in your cereal. Look at this. And they show the same thing, but it's all about the presentation. He puts the magnet up there and like, they're putting metal in your cereal. Your kids are eating metal. Anyway, that's it for today. For those of you online, I know I see you, but don't forget to email me to tell me you were absent, and I'll send you some instructions on what to do next.